We must wait for the. Okay.
Adelante.
Audio.
Ya vino.
Gracias. Gracias. Entonces vamos a empezar. We shall start now again. So good morning to everyone. We start now our work from LAFMAT on this 15th of October. And it's a special day in Brazil. It's the Professor's Day. So my congratulations to every professor on the talk. Yeah. I shall say some words about LAFMAT. LAFMAT is a network, is a Rede Latino-Americana de Física de Matéria Condensada e Ciência de Materiais. And is composed by the University Mayor de São Marcos in Lima, University of Barranca, also in Peru, Lima, Peru, University Nacional University of Colombia. I should say the name is in Spanish or Portuguese also. Universidade Nacional de Colômbia em Bogotá, Universidade Nacional de Colômbia em Barranquilla e Universidade do Norte, todas na Colômbia. Universidade Zulia em Venezuela, Universidade de San Sebastián em Chile e a Universidade Federal Rural de Pernambuco, Universidade Federal Rural de Rio de Janeiro, Universidade Federal de Pernambuco e a Universidade del Norte, em Chile. Bom, a palestra de hoje será do professor Armando Navarro, que é professor da Universidade Federal de Pernambuco. And will be about how material science can help natural product chemistry. Or better, how. Professor Armando Navarro Vasquez is professor at the Universidade Federal de Pernambuco since 2014. Nowadays, he is the coordinator of the material science program from the Universidade Federal de Pernambuco, and he works with polymers and liquid crystals. So, now I will give the word to Professor Armando. Armando, you can start. It's up to you now.
Okay, may you hear me?
Yes. Yes.
Okay, perfect. Just let me share again. Can you see my screen? Okay. So thanks to Professor Albino for the kind introduction. And today I would like to talk a bit about how I ended doing material science, because by formation, I'm an organic chemist. I did my PhD in Santiago de Compostela doing organic chemistry mixed with a bit of computational chemistry. Later on, I started to do magnetic resonance, nuclear magnetic resonance, and right now I combine, let's say, research on nuclear magnetic resonance with the development of new materials which will be or can be applied for magnetic resonance, and then to help natural product chemists in structural elucidation of new compounds. So, just to put everything in context, when we get a new compound, for instance, for our natural cells, imagine this. Are you seeing my pointer? No. for instance, this nux vomica, we will begin with a step of extraction, separation of the compounds using different liquid-liquid extraction technique, HPLC. So you get at the end, you get some chromatography, normally HPLC. And for instance, you detect a compound with this molecular formula. 20 carbons, 22 hydrogens, a couple of oxygen atoms, and 2 nitrogen atoms. Well, this is information that you get, all this ensemble of atoms that you want to connect to get a unique chemical constitution. So this is your problem, the structural elucidation of this new compound. Even if you are able somehow to determine which atoms are bonded to each other, your problem is not finished there. You need to determine the configuration, because every carbon atom with 4 different constituents, as we know, is an stereogenic center. So you want also to determine the configuration of all stereogenic centers in your molecule. So the problem is now even more complicated. You have for a molecule like this is strychnine. In principle, you want to determine a unique configuration. Problem is that by doing magnetic resonance, nuclear magnetic resonance, you can only determine if this is your molecule or could be the opposite enantiomer. So only by magnetic resonance you are able to determine the relative configuration. But this is also already a big step. So today we will talk about determination of relative configuration. I won't talk about how to distinguish between enantiomer safe in the end of the presentation. Well, in many cases, and today we have very good crystallization techniques, you proceed to separation of your compounds, and then you can do a single crystal X-ray diffraction. And then your problem should be, in principle, solved. You have the chemical constitution, you have the relative configuration. Even nowadays, even if you don't have heavy atoms, you can try to get the absolute configuration if you have one enantiomer or another, and you get the conformation in solid state. However, in many cases, the compound does not crystallize because of different causes. Flexibility. The compound is too flexible and refuses to crystallize. Impurities. When you isolate natural compounds, to have them in extremely high purity is a very difficult task. And sometimes the quantity that you have is too small. It's difficult to get these crystals. So you cannot crystallize the compound, you cannot do a single crystal X-ray. There are some recent papers on advances on electron microscopy applied to the determination of organic compounds. I think this is something that will impact very soon the field. I think it's still a bit in its infancy. There are not so many devices that you can use around the world, but it's something that probably will get cheaper, and we will see how electron microscopy can become an alternative for this purpose. So when you are not able to crystallize, then you resort, as you know, to high field NMR spectroscopy to determine, first of all, the chemical constitution. Well, probably most of you have done at some point of your career, study a bit of magnetic resonance. So a magnetic resonance spectrum will give you information about the chemical environment, which atoms surround your nuclei, hydrogen, carbon nuclei, and the fine structure will give you information about the scalar couplings. These multiplicities tell you which magnetically active nuclei are close to each other in terms of the number of bonds that connect them. So you have a lot of structural knowledge, and this structural knowledge you can apply to the solution of your elucidation problem. So the gold standard of, let's say, natural product determination should be the recording of a proton NMR spectrum, and then to resort to bidimensional spectroscopy. So in bidimensional spectroscopy, you have a direct detection period, a T2 detection period, which is normally represented in the horizontal scale, but it's just convention. And then an indirect evolution. You recall a series of experiments with different T1 times. So you have evolution in one dimension and evolution in the other dimension. And you are going to relate this to the existence of scalar couplings, different types of couplings between magnetically active nuclei. So in the cause experiment, you will relate protons that are coupled to other protons. And in this, most of the cases, this is done through 2 bonds or 3 bonds, the so-called geminal or vicinal couplings. So when you see a cross peak in the cause spectrum, you know that you have 2 or 3 bonds. This is a lot of knowledge already. Then you have the HSQC. This is a proton-carbon spectrum. So you know exactly which proton is bonded to which carbon. Very useful information. And finally, and this is something that in most of the cases you will need for less than trivial structures, you have the HMBC. So in this case, you know if a proton is coupled to a carbon at 2 or 3 bonds of distances. Most of the cases, sometimes there are ambiguities and you have what is called the long range couplings. But this is, let's say, the rule of thumb. So recording all these spectra, which nowadays you can do for tiny quantities of natural product compounds, less than 1 milligram, many cases, you put all of these, you open all these spectra, and because you are very well trained in structural elucidation, you solve the problem. You can do it, but a computer can also do it. If you furnish all this information in a proper format to a computer, the computer will use fuzzy logic algorithms, and he will build all possible structures that are compatible with your information. This is it is called the computer-assisted analysis. And from my experience, sometimes it's very useful for compounds that are whose structures are far from trivial. So sometimes it's good to help you a bit with computers. Well, until now, we don't have so much material science here. But I just wanted to illustrate what we are trying to solve. Well, you have the chemical constitution, and then you need to determine the configuration. If a particular stereogenic center has a particular configuration or not relative to the other centers. So for that purpose, you need geometry information on the 3-dimensional geometry of the molecule. And which experiments will give you this kind of geometry information? Basically, 2 classical NMR experiments. The first one is the use of nuclear Oberhauser effects, mostly in 99% of cases, nuclear Oberhauser effect between pairs of protons. Because when you selectively irradiate a proton, you are going to perturb the populations, and this population, these magnetic or these NMR levels, populations will be perturbed, and this will be transmitted through relaxation to the neighboring nuclei. So you are going to detect basically if a proton is close to another proton. Very useful geometry information. This is a local effect, which depends on the 6th power of the inverse of the 6th power of the distance between them. So you have some peak in your NOE or NOC spectrum, you know that your protons are close most of the time. And the other parameter is the vicinal scalar couplings, because the value of vicinal scalar couplings between nuclei separated by 3 bonds depends a lot on the value, or strongly depends on the value of the subtended dihedral. So you know or you have the very well-known Calprus curve. So if you have a large coupling, you know that protons will be at 0 degrees or 180 degrees. If you have a very tiny coupling, you should be between 60 and 120 degrees. So the observation of this coupling, the value of this coupling, will tell you how oriented is one bond with respect to another bond. But this is also local information. You have just nuclei that are separated by 3 bonds. In most of the cases, this may suffice. You are able to determine the configuration and even the conformation of the molecule just with these 2 parameters, the combination of nuclear Oberhauser effects and vicinal scalar couplings. But this may not suffice. For instance, imagine this example. This is ludartin as schitarpine. And this part of the molecule was solved, but then it was not very clear. This epoxide, the hydrogen and the methyl group were pointing upwards, like here, or pointing downwards, like here at the right side. If you look at the distance between the methyl group and the hydrogen, the 2 distances are quite close in both cases. So you're not able to solve the structure. You are not really sure if you have a configuration or another possible configuration. So there are a lot of ambiguous cases that you want to solve in some way. So how to get more information? Well, something that you can use is the dipolar coupling. I was talking about couplings between magnetically active nuclei. But the direct dipolar coupling, which is not directly observed in liquid state NMR, in fact, could give you a lot of information. The dipolar coupling is in fact, it's a direct through space coupling between 2 magnetic dipoles, which depends on the gyromagnetic ratio of the 2 nuclei, inversely depends on the 3rd power of the distance, and depends on this factor, angular factor, which is just the second Legendre polynomial squared by 1/3. So it depends on the angle that the 2 dipolarly coupled nuclei forms with the external magnetic field. So depending on how the molecule is oriented to the magnetic field, this coupling can have one value or another value. So there is kind of let's say that the magnetic field is probing the orientation of the molecule with respect to that field. So for instance, imagine this hypothetical molecule, and you have a dipolar coupling between the proton and this carbon-13. this coupling will be positive because it's more or less placed horizontally with respect to the magnetic field. And this one will be negative. So you can, in principle, distinguish equatorial placement from axial placement. So you know that if one is positive and the other one is negative, one should be equatorial and the other one should be axial. You have proved the relative configuration of these two centers. This is very useful. You can establish geometry relationships between pairs of coupled nuclei regardless of the distance. You have non-local information. This you don't get with scalar couplings, this you don't get with MOE, but you can get it with dipolar couplings. Well, of course, you can tell me, maybe the molecule is not like that, but like that. Still, this one has switched to negative and this one to positive, but the relationship between them is conserved. At the end, what you have is an ensemble of different rotational states. And your dipolar coupling is the time average of all the possible orientations of the molecule. So you have this time average term between brackets. As you know, if the rotation is isotropic, this term just equals 0, just vanish. In liquid state conventional NMR, there is no observation of spectral lines due to dipolar coupling. Dipolar coupling only manifests through relaxation, but does not give you new spectral lines. So what we're going to try is, okay, it's 0, but maybe we can try that is not so far from 0, but still a finite value. Can we get a small angular term for the dipolar coupling and obtain small dipolar couplings? Also, you don't want very large ones. I will tell you later why. So we'll try to get tiny dipolar couplings. How is the way to get these tiny dipolar couplings? Simply try to impose a small degree of order. Slightly orient your system with respect to the magnetic field to get what is called an isotropic rotation. You have a finite angular term value in your dipolar coupling expression. Well, how this is done in practice? As you will see now, I think the roots of the field are nearly from the 60s and 70s, but application to structural elucidation is much more modern. We are talking about for biomolecules like in nearly 2000 and for small molecules even later. So you need to orient to impose rotational order. You can do it using an external agent. And there are two ways to do that. One is to use pneumatic phases, and the other one is to use polymer gels using what is called mechanical straining of the gel. There are different polymer gel systems, different pneumatic phases that you can use for such a purpose. There's also the possibility to use paramagnetic tagging, but I won't talk today about that. Well, in the case of polymer gels, the root of the technique can be traced to this very phenomenal paper, I would say, from Samulski. Samulski is a very well-known polymer chemist and very important contributions. And he published in 1981 that if you get a piece of rubber, swell this piece of rubber in a solvent, in this case benzene, if I remember well, and you stretch the rubber, you observe the following. This is the deuterium spectrum of a deuterated benzene. When the stretching is, or the rubber is not a stretch, you have a stretching factor of 1.0. The rubber is in this natural state. You have just a single line, a single deuterium line. When you stretch the rubber, you see that the spectral line divides into two. Why? Because you have a quadrupolar coupling effect. And this quadrupolar coupling, similarly to the dipolar coupling, depends on the second polynomial legend, depends on the orientation of the C deuterium bond with respect to the magnetic field. So you observe that when you stretch the rubber, you have quadrupolar, a visible quadrupolar coupling. You are oriented your media. This is very well, or that was very well known in liquid crystals. But this was the first paper where it was proved that you can obtain alignment, NMR alignment, using strained elastomers. So this is the basis of the use of polymer gels in structural elucidation. From later on, I think a lot of things were developed, first for mostly for biomolecules. So today, we have a lot of different elastomers that can be swollen and used for the recording of mostly dipolar couplings. So we have hydrogels, gels that you can swell in water, and organic and gels that can be swollen in organic solvents. Hydrogels were easy to find, many of them, mostly polymers based on acrylamide, but organic solvent gels, this was a bit more difficult. So today we have many polymers, and depending on the swelling compatibility, you can use different NMR solvents. You can use polydimethylsiloxane. And polydimethylsiloxane is a quite nice gel, swells in chloroform, swells in benzene, swells in THF. PNNA, this is a pretty good one. You can swell, or it swells very well in chloroform. And deuterated chloroform is perhaps the solvent of precedence in NMR. You have polyacrylamide derivatives that can be swelled in water, but some of them can be swelled in DMSO. And this is very important in industry, because in industry they use a lot of DMSO for doing NMR. So having gels that swell well in NMR, it would be good for structural elucidation problems in analytic departments of pharmaceutical industry. I will tell you about polyacrylamide trial in the NSO. There is a bit old review, but very well written from Louis and Kumerlov in analytical chemistry, that you can see the kind of gels that were developed until that year. So what do? You prepare a stick of a polymer in the most simple way to use these gels. And then you let it swell inside an NMR tube. So you drop chloroform here, close the tube, just let it swell, and the gel, when it swells, will touch the walls of the tube. So it will begin to roll anisotropically. So you have a straining in the axial direction. So your rubber elastomer network is now deformed. And because of this deformation, the molecule that you put along with your solvent will be also oriented. You get a molecule that is solved in your solvent, NMR solvent. You put this analyte along the solvent into the tube, let the gel grow, and then you get an oriented system, a weakly oriented system. We have degrees of order that about one part in 1,000. Well, this is one way to do it. But there's another way that this was developed by Nick Zarevsky and Roberto Hill. Nick Zarevsky at that time was a postdoc in Matiszewski group. Well, not at the time of that paper, a previous one, but I think this, he was a professor when this paper was published. So you can compress the gel instead of letting roll inside the tube. So you get an NMR tube here and a plunger, and you put solvent along with your molecule of interest. Here, the gel has just been polymerized, and you have, let's say, you don't have cavities really in a elastome, but let's say that you have some kind of cavities or a pulse network. You let the gel swell inside the tube. But in this case, you take care that the gel is not so large as to touch really the walls. And then the gel swells freely. You have an unstrained elastoma, and then you begin to compress. And the gel is slightly compressed, and the, let's say, cavities became prolate. So you have mechanical compression, and you have an oriented systems, and you will have dipolar couplings. Well, our first contribution from my group to this field of polymer gels, to this field of polymer gels was the development of a chemically cross-linked polyacrylonitrile. I will take in a few slides a bit more how we synthesize these gels. So basically, we prepare a polyacrylonitrile gel that can be compressed. Polyacrylonitrile was already synthesized by the group of Louis, but through irradiation with beta radiation. And the mechanical quality of the gels, let's say that it was not so good that they should be desired. So we were trying to do another thing. This was kind of a side effect. We were trying to get something for acetonitrile. But what we got was compatible with DMSO. So this chemically cross-linked polyacrylonitrile gel can be compressed and obtain dipolar couplings that can be then applied to structural elucidation. You get, for instance, for strychnine, a set of one bond carbon-proton dipolar couplings. What you get in the spectrum? Well, I will tell you, or I will show you first. This is the spectrum, the deuterium spectrum of the of this DMSO compatible gel. So in the deuterium spectrum, you are going to see the DMSO signal. And you will see two signals. One is the DMSO inside the gel. Since the gel is not touching the walls, you have a bit of DMSO outside the gel. And then you compress the gel. You go from this state to this state, and you compress the gel, and you have a quadrupolar coupling. You observe these quadrupolar couplings, and and you will observe, or you will know that your system is aligned. So you do two measurements. The first one is a relaxed or a measurement in the relaxed state, and you get the scalar coupling. You see also in this HSQC spectrum, in the relaxed state, you will see the signal inside the gel and the signal outside the gel. because the magnetic susceptibility is a bit different and the resonance position is also consequently also a bit different. And then you compress the gel. And the coupling you get is the scalar coupling plus the dipolar coupling. So you just subtract this value from this value and you get the dipolar coupling. You do this for all the spectrum and you get a set of dipolar couplings. Then you do some molecular modeling, try to fit these dipolar couplings, which depends on molecular geometry, to those structures, and you get a result. And normally this is expressed in terms of a scale and a MSD, which is called quality factor. And well, you clearly select the correct structure, in this case of brucine. So we were quite happy with this result. The gels were really easy to use. And I will tell you also that we went in a commercial direction with that. And sorry, what happens here? Okay. So we went, now we were trying to get polymer gels that were compatible with more polar solvents, particularly acrylonitrile, because there were not very good polymer gels for acrylonitrile, and this is something that we wanted to use. Why? Basically because when you measure chirotical properties that are going to be used for assignment of the absolute configuration to distinguish one enantiomer from another, in many cases you use circular dichroism. And circular dichroism, most of the time, you measure for organic molecules in acrylonitrile. So we wanted something that will give us information about the conformation of the molecule before we do the chiroptical analysis, because the chiroptical analysis depends on your conformational space. So we wanted basically to get something for acrylonitrile. This was difficult to do using just a monomer for the polymerization. But we found that mixing monomers gave us a polymer of the appropriate polarity. So we mixed dimethylacrylamide with acrylonitrile. And in fact, when you polymerize, you have also an advantage. That is that the gels are normally less brittle, because the pure monomer gels, many of them are too brittle. And when you use them a couple of times, sometimes they begin to break at the top. So these copolymer gels are sometimes more resistant. And what it was nice to observe that by changing the ratio of the monomers to 70-30, then we can just get a gel that it was good for methanol. So we were able to measure dipolar couplings in acetonitrile and methanol just by changing the ratio of the two monomers. And the range of the dipolar couplings, normally I like dipolar couplings which are between, let's say, 0 and 30 or 40 in absolute value. So it was a particularly good range. How do we prepare these gels in general? Well, in this case, for instance, we get the monomers, acrylonitrile, dimethylacrylamide. If they, normally they are sold with a radical inhibitor, you filter through alumina, but this is not always the case, and you dissolve. Normally, I prefer high boiling point solvents, particularly DNF. Also depends on if the final polymer is soluble or not in your solvent. So for instance, for acrylonitrile, the key was to use DNF. You need a cross-linker. The most simple one is ethylene glycol deacrylate, but you can use another ones. You can try to modify the amount of cross-linker. This is a crucial step. Normally, you need to prepare several gels and choose the amount of cross-linker necessary to produce a gel with the right degree of swelling and size. And then you put a radical initiator, which it's been a bit tough because I don't know why AABN is not sold now in Brazil. So we are trying to survive with the AABN that we have in the lab, but because of quite a stupid policy, it's impossible to buy AMPN. So, well, we just dissolve all of these reagents. We put into a 3mm tube, polymerize in a chamber, normally around 24 hours, 60 degrees of temperature. And then we get the gels, we break the tube, we cut the gels, and then wash with solvent, normally if the same solvent that we are going to use for the swelling, and let the gels dry. And then we put them here, we add the solvent with our analyte, and we put this compression device. That is just a simple Teflon device that fixes the position of the plunger. So just you can compress the gel in different ratios. So these are the devices that we mostly use, but you can do it even with a Shigemi plunger. That's the problem. This is a bit more convenient, but a Shigemi plunger will work perfectly most of the time. I just show you here an acrylonitrile swollen gel. We tried also another solvents, but they didn't work so well. So the better ones were acrylonitrile and methanol. These are just the deuterium spectrum relaxed state. So this is acetonitrile inside the gel, outside the gel, and this is just after compression. So you have quadruple couplings, and in some cases, this is still a layer of solvent around the gel, so you can see sometimes a bit of isotropic signal. So we, as I was talking before, we went from the relaxed state to the compressed state. So this is a general procedure for this kind of compressed gels. Something that we were asked for is if we were able to synthesize water-compatible gels. Well, there are many hydrogels, but not so many with the right mechanical and swelling properties. So we decided, okay, we can go for a copolymerization strategy. So what we did in this case was to do a mixture of acrylonitrile with propane sulfonic, this acrylamide methyl propane sulfonic acid. Polymerizing these two monomers give us a gel that need to be washed with base. In our case, we use just a solution of potassium carbonate, because otherwise you have a very acidic gel, and you don't want that. For instance, if you put sucrose inside the gel, it's nearly instantly hydrolyzed to, sucrose inside the gel is instantly hydrolyzed to sucrose and fructose. Well, this gel works well for carbohydrates molecules or without coordinating groups. But we observe that does not swell well if you have ionic compounds. So you have, for instance, carboxylate or ammonium salts, because then you have saline bridges and they don't let the gel to grow or to swell as much as you need. So the gel have a limited applicability. We are now working on non-ionic gels, and we are getting interesting results, but they are still quite preliminary. So this was our first attempt to a hydrogel, but still we were able to use this gel for some molecules. For instance, saccharose, we were able to get quite clean HSQC spectra, and to even extract dipolar couplings that we could apply for the conformational analysis of saccharose. And we got a conformational distribution that very well match the already reported ones. So I would say that is a gel that you can, without many problems, apply to sugars. And then we found something that I particularly found very interesting, that this very kind of copolymer gel, the methylacrylamide acrylonitrile, you tune a bit the ratio to 75-25, and then you can swell then with an ionic liquid. So we use ionic liquids of the imidazolium family with different counterions. And we found that our gel was swollen perfectly in many of these ionic liquids. This is a very nice result because you have an ionogel that you can prepare very easily, a very straightforward procedure. For the particular case of the butylmethylimidazolium, the cyanoimide gel, you would just prepare the polymer gel, you drop the ionic liquid and you let it swell for a couple of days. You get an ionogel with an ionic conductivity up to 10 to the minus 2 centimeter, which is a very nice result. I think ionic conductivities in this kind of ionogel sometimes are in the order of 10 to the minus 3 to 10 to the minus 4. We're still characterizing all the electrochemistry here, but the results are very promising. So we found let's say a way to easily prepare ionogels that can be in principle applied for uses in electronic devices or electric devices. But in fact, this is not really what we wanted to do at the beginning of this project with liquid crystals. With ionic liquids. We wanted to measure or to determine the structure, the conformation of the ionic liquid, cation. Currently, studies on the structure of the ionic liquid cation is mostly done using nuclear Overhauser effects. So we thought, can we measure dipolar couplings for an ionic liquid which is swelling a polymer gel? Well, this is what we tried to do. So the first ionic liquid we used was butylmethylimidazolium, and with the deflate counterion, you have a nice carbon spectrum. This is just the neat ionic liquid. And then we swell the gel using this particular ionic liquid. And we observe that you can compress the gel in the same way and get dipolar couplings. Not very large ones. Basically, we think because the molecule is rather flexible and the dipolar couplings average a lot, but big enough to be able to perform a conformational analysis. So our first analysis was done using what is called a single tensor approximation, which roughly tells or roughly implies that all conformations share a unique way to align in the presence of the compressed gel. But probably this is a too rough approximation to deal with the conformation of this very flexible and very small molecule. So what we did is to use a more complex procedure which is not based on assuming a particular way of alignment, but it let's say that the size and orientation of the couplings is applied at a restraint into a molecular dynamics procedure. So what we get is what we were expecting from other features of the spectrum and also the computed relative energies, and it's a rather flexible system. So this is very probably the reason that you get a tiny dipolar couplings. But we proved that it's possible to obtain dipolar couplings for ionic liquids that can be later applied for structural analysis. Well, I was talking about polymer gels, and I will be talking now a bit about liquid crystals. And the seminal paper that you need to refer for use of liquid crystals in NMR is this one. And antimatter chemie, there is also a previous one, but I would say that it's maybe the complete or the more complete one. The recent results in the field of liquid crystals by Albert Saupe, sorry. And this was published in 1968 in antimatter chemie. So basically, it was observed that if you put a gas molecule like benzene into a thermotropic liquid crystal, in this case, a liquid crystal formed by these two calamitic mesogens, well, if you are above the clear temperature of the liquid crystal, you will observe the signals from the mesogens, and you have the spectral line for the benzene molecule, just a singlet. But when you are below the clear temperature of the liquid crystal, the signals from the liquid crystal vanish because of the very short T2, a very short relaxation time. They just become so broad that they are just part of your baseline. And you get only the lines of benzene. But because of the dipolar couplings that you observe when you align the system, you get 76 lines, a lot of structural information. Theoretically, it would be possible to use this information to get a lot of information about the geometry of benzene. And in the 70s, NMR of liquid crystal was mostly oriented to the structural analysis of very small molecules or symmetric molecules with this technique. Put the molecule to a thermotropic phase, get very large dipolar couplings in the order of hundreds to thousands of hertz. The degree of order of these thermotropic phases is rather large, nearly 0.1. So you get very large couplings, and you get a lot of strong coupling. These are very difficult systems to analyze. So these thermotropic phases were given a strong alignment, very rich information, but from the practical point of view, okay, this was good to analyze maybe the geometry or the conformational state of butane, but no more than that. It was not really applicable to structural elucidation problems in organic chemistry. However, when you switch to lyotropic liquid crystals, the degree of alignment drops to 10 to minus 3, most of the cases, 10 minus 2 to some cases, but most of them are in the range of 10 to the minus 3. For this degree of alignment, your Doppler coupling is about the size of the scalar coupling. So the spectrum is still a high resolution one and a very simple one. You just extract the dipolar coupling, but get in the spectrum. In the nematic phase, you get the sum of the scalar and the dipolar coupling, subtract the value of the coupling in the isotropic phase. So you get, in this way, the dipolar couplings. A very easy procedure. And then, because of this easy way to do it, you can apply this to complex problems in biostructural chemistry and in organic chemistry structural elucidation, in the same way that you do with polymer gels. a kind of sorry. Of a liquid crystal lyotropic phases that we were very interested were the so-called chromonic mesogens. In these chromonic mesogens, you have a hydrophobic core and solubilized in side chains. The archetype of these phases is this chromoglycate. Chromoglycate you can even buy in the pharmacy. It's a very cheap anti-asthma compound. You can buy for any chemical company, and sometimes, depending on the country, it's even possible to buy it in the pharmacy. So, a particularity of these chromonic phases is that in many cases, they form they have a nematic phase at most ambient temperature, and they have a biphasic region between the isotropic state and the nematic state. So normally we are going to work into the nematic phase to measure the total coupling, and then go to the isotropic phase to measure the scalar coupling. So you need the two measurements to get the dipolar coupling as a difference. At higher concentrations, there is also a so-called M phase with hexagonal symmetry, but the couplings here are too large, and the relaxation times become too short. So it's not mostly of practical interest. So based on previous work from Saupe, we found that, if you mix sodium chromoglycate with brine, then you stabilize the nematic phase, and you need less concentration of mesogen, and you scale down the coupling. So the size of the dipolar couplings became more appropriate for structural elucidation purposes. So we published this a lot of years ago. I was still not here in Brazil. A lot of different molecules can be applied in this way, or measured in this way, in water. We are talking about, in this case, a water-compatible gel. Already here in Pernambuco, my student Clayton applied chromoglycate to the conformational analysis of this alkaloid, monocrotaline. So a good thing is that the clear point is close to room temperature. So what we do, we slightly heat the sample, and we have the isotropic medium. And you measure an HSQC, extract the scalar couplings. Then you drop the temperature. Even here, you can even see the biphasic region. You still have a bit of isotropic phase. But I think the quantity here was small, so we just measure the anisotropic spectrum. Get the dipolar couplings applied to conformational analysis. Well, in this case, we did a similar computational flow theta as for saccharose. We proved, for instance, that while monocrotaline has a zinc orientation of the carbonyl groups in water, if you measure using polymer gels in apolar solvents, then you get a 100% of the anti-apolar conformation. So we applied several solvents, but in water we resorted to this chromonic solvent. And then we start to play with another family of chromonic mesogens, which are BPIs. BPIs are very well known for self-assembling studies. So BPIs prepare by conjugation with amino acid. And this is one of the last ones we have prepared, which is just the derivative of conjugation with glycine. And we got a very nice degree of order in the system. So at low temperature, you get an oriented nematic phase. We went to this biphasic system appears briefly at 35 degrees, and from then 40 you get a completely isotropic system. So just by slightly changing the temperature, again you can measure on the nematic, in the nematic or anisotropic state. We again measure the HSQC spectrum in both conditions, got the dipole couplings, and applied this using a computational model that was developed by us to the conformation of saccharose. So we got a similar result. An interesting thing is that you could prepare BPIs, chromatic mesogens, that are chiral in nature. So you can, for instance, conjugate with an L-valine. And we will start to play with this mesogen to prepare water-based pleiotropic phases. We found that the following thing. When you hit this system, look again at here. Here you have a quadrupolar coupling in the nematic phase, and you start heating. But the size of the quadrupolar coupling does not change with the temperature, or very slightly change. And then suddenly you begin to see the isotropic phase. So this is not a continuous process. You have a mixture of the two phases in some region, and the degree of splitting is fixed, the degree of order. Here, when you hit the system, you begin at 14 degrees with a certain degree of splitting, certain degree of ordering of the system. The splitting reflects the ordering of your solvent. And then the size of the coupling begins to drop until you get a nematic. This is a completely different behavior. And we are trying to understand why this mesogen behaves a completely different way than the other chromatic phases. And this is something that we don't know yet. We are trying to do microscopy. We are trying to collaborate with a group on data in terms of computational simulation of these systems, but we don't know what this system behaves differently. And a nice thing is that when we put saccharose into the system, the biphasic region close to here was stabilized. So we could see isotropic and anisotropic together. And because the dipole couplings in these systems are relatively large, we were able to measure the dipole couplings in the biphasic region. One single spectrum, you get the isotropic and the anisotropic signals. So this is very convenient because you have exactly the same temperature. And in chromatic phases, in principle, the solvation conditions compared to other allotropic systems are very similar into the isotropic in the anisotropic phase. So this is a good procedure to do fine conformational analysis. And even more, the phase is chiral. So what we observe is that if you put a racemic compound and you are in the anisotropic nematic condition, you observe different signals in the carbon spectrum for different enantiomers. So you are doing enantiomeric resolution. In this case, through what is called the residual chemical shift anisotropic. In the same way that anisotropy causes a finite value of the dipole coupling, anisotropy causes a finite change in the value of the chemical shift. This is called the residual chemical shift anisotropic, a small part of the anisotropy of your chemical shielding tensor. So in principle, this can be applied for determine the enantiomeric composition of mixtures. All these endeavor has, in fact, allow us to open a small company inside the let's say the polo technological center of here in the UFPE, and we are just in the process to sign a contract with Mestrolab Research to furnish them with polymer gels. Mestrolab Research is a very well-known company in the field of magnetic resonance in the small molecule field, pharmaceutical companies, nearly anyone doing NMR in organic chemistry. And we are signing a contract to furnish them with polymer gels in principle, but possibly also mesogens, so they can offer to their customers for the measurement of these anisotropic NMR properties. I think I will stop here. I was going to talk a bit about graphene derivatives, but I think it would be a bit too much. So, sorry. Just to acknowledge all the financial support from CMPK, CAPES, and FASEPI, and my group for all the nice research that I was able to write, thanks to their really good effort in the lab. So Diane has prepared a lot of polymer gels. Danilo is working with all the BPI derivatives. Fernando is always helping me with the direction of the group. Gabriela is preparing new graphene derivatives that come from lysotropic phases, also Saturnias. And Clayton, he worked a lot with a kind of a lysotropic system that I was not talking today. Also, he did the measurements on monocrotaline. So thanks for your attention. And if you have any question.
Okay, can you hear me?
Hi.
I thank you very much, Armando, Professor Armando Navarro, for the very nice and interesting talk. Before asking the panelists last question, I have to make some announcements. I sent via chat the upcoming colloquium to the end of this year and starting next year. Okay, I think Dr. Luis Valadares will talk about this at the end. Okay, so again, this network is formed by the Universidade Nacional Maior de São Marcos, em Lima, Universidade de Barranca, as duas em Peru, desculpe, Universidade Nacional de Colômbia, em Bogotá, em Barranquilla, Rio do Norte, na Colômbia, a Universidade de Zulia, na Venezuela, o Centro de Investigação de Materiais Avançados, no México, o CIVESTAF, também no México, a Universidade del Norte, em Chile, e a Universidade de San Sebastián, também no Chile. No Brasil, nós temos a Universidade Federal Rural de Rio de Janeiro e a Universidade Federal de Pernambuco. Bom, vamos abrir para as questões. I would like to call Professor Stuart Holmes. Stuart, do you have a question?
Thank you, Armando. Very detailed talk, a lot of information, which is not exactly my field, but I will ask some questions. Thank you. Do you ever use, when you're trying to understand a structural...
Okay. In fact, this is we use DFT in two ways.
Yeah.
The first one is sometimes because when you do the configurational of conformational analysis, you need the structures. So sometimes we use DFT to generate the structures. The first step is always some force field based generation of the structures and conformational search. In some cases, we just use directly the structures from the force field computation, but in other cases, we use DFT optimized ones. And then DFT can enter in two ways, or in other two ways. The first one is when most of the work we do is with only the dipolar couplings. But in principle, you can also measure residual chemical shift anisotropies, which is a bit more involved technically. But for residual chemical shift anisotropies, you need to know previously the chemical shielding tensor. So you need to determine these chemical shielding tensors at the DFT level. So in case we are going to use RCSAs, we need to use the chemical sheets that have been previously computed. And finally, when we are going to determine the structure of a new product, sometimes what I particularly like is to combine the dipolar couplings with isotropic chemical shifts, and we fit everything together. And in many cases, this gives you the highest degree of selection between different structural possibilities. So there are a lot of points where DFT enters the, let's say, the protocol.
Yeah, thank you. The other question I have is, I think you mentioned it very briefly, but are there any materials from medicine or from the pharmaceutical industry that would benefit from this very detailed structural and chemical analysis? I assume the people that make the medicines are knocking on your door. I assume.
In fact, there are many people that particularly. In fact, it's a curious question because the use of dipolar couplings is more popular in pharmaceutical companies, that they use this, for instance, not mostly, for conformational analysis in polar solvent, DMSO, water, for instance, conformation of peptides, conformation of any kind of drug. So I have I think I also work on the computational part of this, and I have a lot of collaborations with pharmaceutical companies. The thing that we are, let's say, not only me, but also other people in the field are a bit disappointed is that natural product chemists, I think there are a few groups that work a lot on this. For instance, some groups from China, they use this technique a lot, but it has not become so popular as I think it should be in the natural product field. Because I think that the technique is simple enough that at least you record a set of dipolar couplings and will avoid you to make very mistakes that you do, because they like a lot, for instance, chemical shifts, but they don't like so much aligned median MR. So it's a bit we're a bit struggling a bit with the natural product chemist community. So at the end, the goal of my research is to simplify this as much as possible, as to really to be able to provide them with something that is really so simple as to make a difference for them.
Thank you. Thank you, Professor Navarro. Thank you.
You're welcome.
Thank you, Stuart. And now I would like to call Arturo Martinez from Cinvestav, Mexico. Arturo. Arturo? We are not hearing you. No te escuchamos, hombre. You see, Armando, here we can speak in any language.
Yeah, multilingual. Aquí dice que se le fue la internet. No sé si tal vez tuvo problemas de nuevo.
Okay, let's ask another. Luis.
Hello.
Luis, are you there?
Yes. Hello, Armando. How are you?
Fine.
Well, actually, I don't have questions in this moment because I joined it in the last minute. However, I think that is a very interesting talk. But as I want to take advantage to mention that you know that one news about this network that Professor Albino Aguiar and Professor Arturo Martinez from Mexico, now they are joining the board of the journal Heat Treatment and Surface Engineering of Taylor and Francis online. Congratulations to Albino and also to Arturo Martinez from the same staff. Okay.
Thank you, Luis. It's supposed to be a secret for the moment.
It's no longer.
Congratulations, Arturo.
Parabéns, Albino.
Gracias.
Aos dois pela nomeação.
Vamos a ver ahora. Oh, sorry. Sorry. Let's ask people from Colombia if we have questions from people. Eliana, are you there, Eliana? Ximena? Eliana, welcome. Bienvenida.
Obrigado.
Gracias, Eliana. Ximena.
Buenos días a todos, buenos días, profesor Albino. En este momento tampoco tenemos preguntas por acá. Solo nos dejaron aquí agradecimientos por, obviamente, el tópico interesante de la charla y por muy buen todo el proceso que se está realizando allá. Nos dicen aquí los estudiantes. Muchísimas gracias por la charla del día de hoy.
Gracias, Ximena. James, tenemos preguntas del público de Perú. Por favor.
Saludos, profesor Albino. Saludos, profesor Armando. Por aquí no tenemos preguntas, solo felicitaciones por su presentación. Gracias.
Gracias.
Okay. Arturo is informing that he has problems with his computer. Okay. Armando, let me ask you, how about using your NMR technique to helping people for working in inorganic crystals? What can you do for the people from this network?
I think there is a possibility to use this. I think we are talking about liquid state NMR in principle. So in fact, this is something that I really very interested, and this is something that we are doing now, and is to be able to use this for inorganic compounds. Mostly, I think there are a few examples of using dipolar couplings for inorganic compounds in several ways. I think you can, for instance, palladium complexes, you can use it. Sometimes you have compounds that are paramagnetic. And then the dipolar couplings, they arise naturally because your compound is already aligned in the magnetic field because of the anisotropic magnetic susceptibility. So you get relatively large dipolar couplings even without the need for an alignment medium. So it's possible to do that. With respect to solid state, that's a different question, but this is something that I talk sometimes with NMR spectroscopies, and there are some techniques that you can measure small or reduce the size of the Doppler coupling, doing off-axis techniques in solid state. We are not so familiar with that. Also, we don't have, I think, the equipment for doing such elaborate solid state experiments. But in principle, is something that theoretically is doable. But in solution state, it's directly applicable. And sometimes even if you have paramagnetic ions, you can get very good data because you get the Doppler couplings and you have the pseudo contact shifts. And you put everything together into the analysis. And it's a very nice way to obtain structural information. So there's a lot of things that you can do for inorganic chemistry, but mostly for liquid state.
Okay. Thank you, Armando. Let me mention you that we have very some people here in the network, they are very high specialized in electron microscopy. Maybe you can talk with them. I'll ask Luis to comment on this. Luis, can you comment about the people who is highly specialized in electron microscopy in the network?
Yes. We have also Paraguay, Professor Paraguay, for example, who is the leader of one lab in all the kind of microscopies. That unfortunately today is not here, but he works in Mexico in the National Institution of Material Science in Mexico. I think that Arturo knows him very well, right, Arturo?
Arturo is with computer problems.
Okay, no way. Well, they also many people here knows about those techniques. Most of us in this network, we use electron microscopies in order to show in our papers our devices or samples, the microstructures or samples, morphology, etc. Well, that is the case. Well, Albino, you tell me when I announce the next speakers. I would like to take advantage of that. Okay, Armando, you know that this network is a network which members are from different universities in Latin America, and we invite speakers for all Saturdays. You are invited to participate in the next talks. For example, today your talk has been Professor Bagop was attending this talk today, right, Albino? I saw him today, right?
Yes.
But he left.
He left.
You are invited
he disappeared now.
Yes. But next Saturday, Sergio Resende is going to give a talk on Saturday. Sergio Resende from the Universidade Federal de Pernambuco.
Sí.
On Saturday, 29th of October, José Luis Ochoa from the Venezuelan Institute of Research Center. His talk will be Propiedades eléctricas y modelos de percolación aplicados a mezclas conductor aislante. José Fermín will be the moderator. On November 5th, Dr. Adrian Ionescu from the University of Cambridge. He's going to start his talk from 9 a.m. Peruvian time, so half an hour later that you will usually meet. November 12th, Professor Diego Lamas from Argentina. The moderator will be David Landinés from Colombia. November 19th, Professor Edson Sardella from the UNESCO, and Isaías Gonzaga Oliveira will be the moderator. November 26, Sergio Conejeros Espindola from the University of Antofagasta in Chile. The moderator will be Arturo Martinez. December the 3rd, Leopoldo Suescun from Uruguay. Professor David Landines will be the moderator. On December the 10th, Alexander Polasep and Isaías Gonzaga Oliveira is going to be the moderator. And finally, the last talk for this year is on December 17th. Carlos Santos from the USP, University of Sao Paulo, and the moderator is going to be Professor Albino Aguiar. After that, we are going to have some holidays for Christmas and New Year, and then we are going to continue next year. We are going to continue the new talks. Well, and I want to announce also from this network that Ximena Velázquez is going to travel to Cambridge on February for an internship for 6 months, and she's going to work with the TFN group there, and also Stuart Holmes will help us as well to work with Ximena. Well, that's and also one student from the University of San Marcos, Henry Sanchez, who is the University of San Marcos in Peru, is sending the student Henry Sanchez next year to travel to Cambridge as well. Okay, that is the news. Thank you.
Thank you, Luis. Arturo, Armando, are you there? Okay.
Yeah.
Luis, let me mention that you forgot to say that in December 24th, we are going to have the talk from St. Nicholas, yeah? Directly from Spain. Yeah? Okay. So, just to finish, let me mention again the university of this network, University from Peru. Nós tenemos la Universidad Nacional Mayor de San Marcos, que es la decana de las Américas, la Universidad de Barranca. En Colombia, nós tenemos la Universidad Nacional de Colombia, en Bogotá, en Barranquilla, y la Universidad del Norte. En Venezuela tenemos la Universidad del Zulia. En México, nós tenemos los Sinvestaf y los Centros de Investigación de Materiales Avanzados. En Chile tenemos la Universidad de San Sebastián en Puerto Montt y la Universidad Católica del Norte en Antofagasta. En Brasil tenemos la Universidad Federal Rural de Rio de Janeiro y la Universidad Federal de Pernambuco. Bueno, with this, I ask everybody to open the camera and say goodbye to Armando, and ask Armando if he has some final words.
Thanks, Albino. So it was really a pleasure. I really like it to be able to talk here in the seminar series. I think I will try to really participate more. Sometimes Saturday morning it's not always so easy for me, but I will try to do my best. I think I really find a very interesting community, and I will forward for the talks. I really appreciate the invitation.
Thank you again. Arturo is coming back, and he said before, congratulations for your talk.
Thanks.
So again, thank you, Armando, and have a nice time. Gracias.
Buen final de semana. Buen final de semana a todos.
Chao.
Ciao.